Okay, so this is applications of polynomials, and we have our first one, which is a polynomial, but this is our parabola. It says the price demand equation for an 8,000 BTU window air conditioner is given by this, where X is the number of air conditioners. So anytime they tell us, we need to write it out. Number of air conditioners. And P is our price in dollars. So we know now that if you plug in some X, which is the number of air conditioners, it tells you the price that they would charge to sell that many air conditioners. So there's also some price that they would charge to sell some number of air conditioners. Okay, so what are we doing with this here? It says find the revenue function. Okay, so revenue is always price times quantity. So if you think about it, we're selling a price for an air conditioner, and we're multiplying that by the number of air conditioners. Like if you charge $100 for an air conditioner and you sell 1,000, it'd be $100 times 1,000 to get your revenue. So all it is P times X. So if you take your price function, which is 0.0004 x squared minus x plus 569, and you multiply it by the number of air conditioners, x, you end up with a revenue function in terms of x now. That is 0.0004 x cubed minus x squared plus 569 x. So we now have a function that represents the number of air conditioners sold and the revenue they would bring. And again, these number of air conditioners sold are affected by the price. So you basically have some price that would tell you the number of air conditioners sold that would then tell you the revenue, or vice versa, the number of air conditioners sold, which tells you the price, which also tells you the revenue. But long story short, this is our revenue function based on this demand equation. So if we take this and we plug it in our calculator right here, and we're supposed to start with zoom 6, right? And you'll see that we get really nothing. Yeah, it's still graphing, but there we go. So we already know that if it has a leading term of x cubed like that, we know its end behavior looks like this. And it has 3 intercepts, right? Max. So it either does this, is the most likely the graph that we're looking for. That's what we want to find. So we want to keep modifying this. And the best way to do that is you click on Window, and you put in a realistic domain here. So we know we can't sell less than 0 air conditioners. X is the number of air conditioners. And we'll probably sell a lot more than a lot of air conditioners. So if we put in a realistic domain, put zoom and 0, zoom fit, it'll fit over that. So that's 0 air conditioners, that's 2,000 air conditioners, and that's the function we're looking for. Okay, and so now what we have to do is get a realistic domain off of this. So if I hit trace and move it back, yeah, I'm going to start there, stop there. So you can see that this is our revenue. Our revenue is increasing as we sell more air conditioners. So you keep selling air conditioners, the revenue goes up. And then as we keep selling more air conditioners, the revenue comes down. And what happens here is the revenue turns negative. What that means is in order to sell this many air conditioners here, we'd have to give them away. We have a negative value and pay people to take them. So that's not possible. So right there is the final end that you can go. You can't go past 0. So what we have to do is find out what that point is. So that's where second calculate. The zeros come in that we used our calculator for before. So number 2, we want to go to the left of it. So just scroll to the left. Now we're at a number left of it. Hit enter. Scroll to the right until we're to the right of it. Hit enter. And then hit enter, and it tells us what it is. So 875.8. So I would just say 876. That's as far as you can go. So our realistic domain here is from 0, less than or equal to x. And I'm going to put the decimal in there. Less than or equal to 875.8. 875.83. So this is our domain, air conditioners. And this is our revenue function. Now, what's the one thing you want to do with the revenue? you want to maximize it, right? So it says find the number of air conditioners that must be sold to maximize the revenue, the corresponding price P, and the maximum revenue. So we need to use and find this, and you can use this or you can use Desmos. It's your choice. And so since I already did this one, we might as well just stay here. So second calc, maximum number 4. And now we just use that domain. So we know the left bound is 0. The right bound is 875. And then we guess. And it says the max is 364. So 364, comma, 93911.42. 93911.42. And then what does this represent? This was our X, which is the ACs. This is our R, which is the revenue. And it's also in dollars because our price was in dollars. Right? And it's dollars each. Okay. Because it's dollars each. So let's answer our question now. Find the number of air conditioners. So 364 air conditioners to maximize the revenue. So we would get the max revenue of, we don't need of, I put the little dots, 93911.42. So $93,911.42 is our maximum revenue. And so now what's the important thing is what price do you sell it for? Well, you already have the X, so if we go back and we plug our X into the top function, it tells us the price. So our price of 364 air conditioners would have to be what? So how much do you need to charge so that you will sell 364 air conditioners and have a maximum revenue of $93,911? So we would have to charge $258. I'm going to round that up, right? So $258 is what we would have to charge. That's our price. That would be the revenue, and 364. So the way it works is you charge $258. They sell 364 air conditioners. Total revenue is $93,911.42. Now there's a little different way of doing it as well. Well, the ending part anyways. Think about it. If you take that 258 and you multiply it by 364, you're supposed to be getting this. So if I put times 364, what do I get? $93,911.42, which is what we have here. So you could also just take this price, this revenue, divide it by the number of air conditioners, and it gives you the price because remember, price times quantity is revenue. All right, let's try another one. So it says the greatest length of U.S.-owned operating railroad track existing in 1916 when industrial activity increased during World War I. The total length has decreased ever since. The data over the years 1900 to 2011 are modeled by the quartic function, because we have a degree 4, where x is the number of years after 1900. So we should write that. X is number of years after 1900. Find the number of miles of operating railroad track in the United States in 1916, 1960, 2000, and 2016. Use the table function. So we have 1916. This would imply an x of equal to 16. 1960 would be an x equals 60. 2000 is x equals 100. And 2016 is x equals 116. And so they want you to use a table function to find this in your calculator. So all we have to do is plug it in our calculator and simplify. All right, now I know it says to use a table function, but they don't know what we're using. So an easier way to do that is to take your calculator and to get this type of a graph and use a trace function. So I've already entered it in, and you've got to be very, very careful with this on how you enter it. But then we go again and we look at our real domain. And so I put 0 to 116 because the values we're looking at are from 1900 to 2016. So that would be from 0 to 116. And then again, we use the zoom fit, zoom 0. What it does is it fits our graph perfectly within that 0 to 116. So this represents 1900, and this represents 2016. And now we can just use the trace function. So our first number we're going to plug in is 16, and then 60, and then 100, and then 116. So if we go trace and 16 and hit enter, it tells us the answer. So 246595.5. So I can remember that. 246, nope. 246595.5. 246595.5. And so now if we just do that for each one, we're going to hit trace 60. It's now 211, and you can see that the number of railroad tracks are going down, that it increased, and then now it's going down. So 211,619.52. 211,61, I already forgot. 619.52. And then we're just going to do this again for 100. So trace 100, and it's 145,886. 145,886.75. Remember correctly. 77. And then now again for 116. Trace. So 133,079.62. 079.62. And again, what does the f of x represent? Miles. So our f of x, our y value here, is miles. So each of these is miles of track. That's it. So it's always using that fit a good domain with your x min, x max, and then you hit zoom 0. That's it. So if you always have a good domain, like we started up here, and you hit zoom 0, it'll give you a good picture of it. Okay. Last one that we have here, an open metal chemical tank is to be made from a rectangular piece of stainless steel that measures 10 feet by 8 feet by cutting out squares of the same size from each corner and bending up the size. Sound familiar? So we have some rectangle, and we're going to take and cut out the corners. We're going to call that x, and x, remember this is the same problem we did. This is the box problem, but this time we're going to be making that chemical tank again. Right? And so this is 10. So again, 10 minus 2x, and this is 8 minus 2x, because as you fold this up, that's horrible. Let's try that again. That looks better. All right. So that's the inside. We get this box. And so as you fold these sides up, we get x for the side. And then removing that x and another x, you get 8 minus 2x. And, oh, I got them backwards. 10 minus 2x and 8 minus 2x, which gives us a volume of 8 minus 2x, 10 minus 2x, and x. But we're going to be doing this one all by hand now, because I want you to think about how would you use the zeros. So what is the domain? And so the time, use the zeros. This time use the zeros of the polynomial to determine the domain and draw a rough sketch of the desired region. So think about it. What are our zeros here? So for the first one, it would be 8 divided by 2. Remember, each of these has to be 0. So the first one would be 4, because plugging in 4 would give us 8. 8 minus 8 is 0. Here would be 5, and the next would be 0. So putting those in order, we have 0, 4, and 5. And our leading term here would be negative 2x times negative 2x times x, which is 4x cubed. So we know that our end behavior is this. So we can do our rough sketch like this. And then now as we connect it, we know our graph will go up. It has to cross back through 0 and then come back up. That is our only way because we have a cube here. So those 3 zeros are it. We can only have at most 2 turning points. So if you think about this logically, right? Realistic situation here. Our box, our x, has a height. Our height of our box is 0. And then the height of the box would go to 4 because this is our volume and our volume cannot go negative. So we are crossing this region off and the only thing that we're counting is here. So that means our domain for this problem would be between 0 and 4. But if you remember last time when we did this problem, it was just you take the longest side and cut it in half. So if that was 8 feet, you can't cut more than 4 feet from each side or you remove the entire side. So it's from 0 to 4 based on our polynomial. So now if the volume of the box is 48 cubic feet, how large of a square should be cut from each corner? So how does this work in a calculator? So I've plugged it in. There's our left side and there's our right side, or vice versa, right and left. And then we go to our window and we do our x-min from 0 to 4 because that's the only feasible region for that box. And then we hit zoom and 0 and it's going to graph our graph that we need. It'll graph that perfect only region that we have, because remember it's going to hit 0 here and then go negative and then go back up through it. And so these are your points of intersection. So if we use second calc and then intersect number 5 and you select the 2 functions and then hit enter, it'll give us that answer, which is 2. And then we do it again. So first function, enter, yes. Second function, yes, I want that one too. And then now we need to either scroll or enter our guess. You can see the x value changes as I move. So this is our other point of intersection. Hit enter, and it says 1. So it's 1 and 2. So if we cut out a 1-inch or 2-inch from each corner, we would have a volume of 48. You can see our volume increases until the max volume and then comes back down. So anything less than that 48 here is going to have 2 different x values that you can cut out to get that dimension. And that's all of our applications. Thank you.